I'm very excited to share with you some recent work in our lab that I feel is a major advance in our abilities to use multidimensional solid-state NMR to learn about the structure of glass. This new advance is primarily the work of Dr. Deepansh Srivastava, who's a postdoc in my lab here at Ohio State, and this work was supported with funding from the U.S. National Science Foundation. Now, before I get into the details of this approach, let me give you a little background on our motivation and goals for developing this new methodology. Now, when it comes to the importance of glass in society and technology and even in the arts, the two things that are really play a big role in that importance is that, one, its shape can be controlled during that melt quench period, and a glass can be formed into pretty much any shape you'd like, particularly if you're skilled like this gentleman here. And the other important thing is that the glass composition can be varied nearly continuously, allowing you to tailor properties in a very continuous fashion. These two properties of the glass are really what drives a number of technological applications for glasses. And of course, there's the obvious ones like container and window glass, but there's all these other types of applications ranging from bioglass to nuclear waste to all of the substrates that are used in electronic devices today. Now, what's important when you're thinking about designing glasses is that you want to be able to think about all of these macroscopic properties like the strength, the hardness, the chemical durability, transparency. All of these are important role for various applications up here. Additionally, when you're manufacturing glasses, you also worry about things like viscosity, liquidus temperatures, and all of these macroscopic properties are a direct result of the underlying microscopic structure, which unfortunately we know some, but we don't know as much as we could know about glass structure, and so that's sort of a hindrance in trying to find better ways to improve properties and get the kind of tailoring that would help many of these types of applications. Now, from an NMR point of view, we're interested in our ability to get local structure, because that's where NMR excels, of course. And so we're going to be interested in seeing what we can learn about the structural distributions, so the statistical distributions in these first coordination sphere structures, so bond lengths, types of polyhedron that are present, bond angles between polyhedra, and so on. Additionally, if we work harder, we can get information about second coordination sphere distributions, so things like the different types of polyhedral unit connectivities, and maybe if we're even luckier, we can get out to third coordination sphere statistical distributions, and maybe hopefully one day we can even learn more about intermediate range and so on. So the general idea then with NMR is to try to focus on exploiting NMR to its fullest to get these type of structural distributions so that we can get a better understanding of how the structure correlates with those macroscopic properties. I'm going to go and give you a very simple example here of just silicon-29 magic angle spinning on this simple binary composition of sodium silicate here. And this is work that goes back to 1996. And this is sort of very typical what you see when you're doing silicon-29 and silicate glasses. You'll see that there are bumps, so to speak, that you can resolve in the spectrum. In this case, based on these chemical shifts, so we can resolve them into what's assigned a Q2, Q3, and maybe here a Q4 site here. And for those of you who aren't familiar with this terminology here, this is the type of tetrahedral unit that's present in the silicate network. So we'll describe Q4s, which are fully connected tetrahedra. And then we have a Q3, which is connected with 3 bridging oxygens to the rest of the network, and one of the oxygens is disconnected. Here's a Q2 where only 2 oxygens connect to the network and 2 are disconnected. They're coordinated by the, say, in this case, the sodium cations. Q1 has 3 disconnected and only connected to 1 oxygen connected to the network. And then we have completely disconnected Q0s here. And so you can see from their isotropic chemical shift assignment where these peaks lie, but there's a lot of hidden details underneath these broad lines. And we were trying to figure out if there are ways that we can learn more about variations in structures of each of these different types of sites. So what we did back then was we had this idea of doing an off the magic angle spinning experiment where you can see very clearly for these sites that they have different chemical shift anisotropies. And that's just simply a result of the fact that when all 4 bonds are identical in length, then you have no anisotropy. That's the case for Q4 and Q0. Here they're all non-bridging, here they're all bridging. But once one of those bonds changes in length, so the NBO, the non-bridging oxygen bond, is shorter in a Q3 than the bridging oxygens, that causes an increase in shielding along that bond direction, and that leads to an anisotropy pattern like this one. When you have 2 disconnected or 2 non-bridging oxygen, here you get a pattern like this, which is what a Q2 looks like and when you're at 90 degrees, and here's what the Q1 looks like in 90 degrees. And so this gives us another way of trying to characterize these different sites. So what we did was a 2-dimensional experiment where we correlated magic angle spinning with off magic angle, and you can see really nicely in these plots here how you can easily distinguish the Q4 from the Q3 from the Q2. You can see them also in this contour plot, and this gave us actually about an order of magnitude improvement in quantifying the different types of sites that are present in this material. Now this was 1996, but if you go forward about 20 years later, we are able to do these type of measurements routinely now at natural abundance, so we're no longer having to do enrichment with silicon-29, and we do that through the use of CPMG acquisition and doping with copper, which helps reduce the T1s without killing the T2s, so we can still do the CPMG acquisition. And now you can see that we can systematically look at various compositions and try to get insight about the structure, not only from the isotropic spectra, but now from the anisotropy that's contained in the spectra. And one of the things that we learned was that for the Q3 site, there's a systematic decrease in the shielding anisotropy as the modifier cation, the cation that's breaking up the network, increases in its cation potential. So here you see a plot of the Q3 anisotropy as a function of modifier cation potential. Here you see cesium, rubidium, potassium, sodium, where they have the highest anisotropies, but when you get to the really high potential cations like magnesium, then you can see the potential is going down. And that's the anisotropy is going down. And that's actually pretty understandable when you think about the fact that cesium, which has very low cation potential, doesn't do a very good job of pulling on that non-bridging oxygen. So that bond length is pretty short compared to these bridging oxygens down here. Likewise, when you think about a magnesium, it's going to be really strong in pulling this, and it's going to pull this non-bridging oxygen out to lengths that are very similar to the bridging oxygen lengths, and so this becomes more of a perfect tetrahedron, and that's why it drops over here. So we see this progressive change as the strength of the cation increases. You also see that the bond length will be increased as you increase the number of cations, and that explains some of these drops here as you increase the amount of modifier that's present in the glass. So that allows us to sort of come up with relationships, and this is a little crude, but it worked. In some ways, it gives us reasonable answers that these are the silicon non-bridging oxygen bond lengths in these different glasses using this formula here, and it's really just dependent upon how much there's a deviation between the bridging and non-bridging oxygens. Now, one of the challenges that we had in trying to fit all of those spectra was that we needed an explicit model for the distribution of NMR parameters for the Q4, the Q3, Q2, whatever sites that were present there. We had to build into our least squares nonlinear fit explicit models for how those parameters might vary in order to fit these spectra. And this was very painstaking, tedious work that Jay Baltusberger actually did all this work, which is described in these 2 papers here. And the general approach, and it's just many people do this, is that you assume that there's some kind of model distribution for the NMR parameters. It could be Gaussian, multidimensional Gaussian distribution of zeta and eta, or it could be like a check distribution for zeta and eta, or maybe you do some MD simulation and use ab initio calculations and you try to get some kind of model for this. Either way, you build some model for the NMR parameter distribution, you simulate the spectrum, you compare it to the experimental data. If it works, great, then you have your parameters. But if it doesn't, then you have to find a way to improve the models and continue until you get your best fit distribution of NMR anisotropy parameters. And so the nice thing about that is that that's a well-posed problem. You can certainly work that out, and you can eventually converge on something that might give you a good fit to your spectra here. But the problem is that any model that you build will very likely bias your distribution because of the way you built that model. So that's going to cause some kind of deviations from the experimental line shape that if the model doesn't have the flexibility to handle it, then you won't get the best fit, and maybe you're going to miss some details that's in that anisotropy. What we're trying to do now is, or what we have done, is we've found a way to fit these spectra without any explicit model for the distribution of the NMR parameters. And the way we've done this is as a linear least squares minimization, where what we're doing is we're building a kernel function of all the possible anisotropic line shapes, and we're trying to invert the spectrum, experimental spectrum, to get the distribution of parameters that leads to the experimental spectrum. So this approach, which I'll give you more detail in a bit, is model-free and it will be unbiased, but the problem with is that this inversion, taking the spectrum to get these parameter distributions, is an ill-posed problem. So the way you would think about this is, as a linear problem, you would say, okay, I have my anisotropic cross-section here, and I know that it consists of many contributions added together with various weights. I can find a way to decompose this into all of the weights associated with these basis subspectra. So this is what we're after here, and what we need to do is just sort of expand a grid of predefined basis spectra for all the possible eta and zeta values that could occur in our spectrum, and then try to do this inverse problem. Now, one of the challenges we had before we even got started was that there's a problem with this convention of zeta and eta, and also with this convention of span and skew. Either one, there's a problem. And the problem is that, one, that the eta becomes undefined when the anisotropy parameter, zeta, goes to 0. So if you tried to make a grid of zeta and eta values and then calculate for every point on the grid a spectrum and use that in your inversion, you run into a problem, because here at zeta equals 0, all of your eta values along that line are undefined. So this is a problem. And then the other problem you have is when eta goes to 1, then you can no longer distinguish the sign of zeta. There's a degeneracy, and so what you find is that for eta equals 1, we have all of these positive and negative values of zeta have exactly the same spectrum. So this gives us sort of parallel basis subspectra, and this is not a good grid to use if you want to try to invert the spectrum. So we had to come up with a better grid, a better sort of convention for describing the anisotropy parameters. So we came up with this convention we're just calling the XY convention, where we're just creating sort of a piecewise polar coordinates. And in that approach, the anisotropy just becomes sort of the R in this polar coordinate system here. So the magnitude of the anisotropy just tells you how far away from the origin you are, is how big the anisotropy is. And then the angle is going to be related to eta. So when eta is equal to 1, you're at 45 degrees. When eta is equal to 0, you're going to be either at 90 degrees or at 0 degrees. And this side is going to correspond to positive zeta. This side will correspond to negative zeta. And this has the advantage that, first of all of those degenerate spectra all now lie on the same line, the same point on this grid. And all of those undefined etas get sent down here to the origin at one single point. So this gives us a sort of more robust grid that we can use in doing our inversion. So we'll be using this for the rest of the talk. We may come back to this here a little later. Now, the way that this works then is we'll take all of those basis subspectra. So we take this grid and we make a spectrum for every single point on this grid. Then we can take each one of those spectra and we can make them the columns in this matrix that is what's called the kernel matrix. So this is just one big matrix which gets multiplied times your probabilities to give you your observed spectrum. And this is what's called the forward problem, where you just take the kernel times the probabilities to get the spectrum. And the inverse problem is to invert this kernel, multiply it times the spectrum to get the solution. Now the problem is that this this matrix is going to be ranked deficient, and so there won't be an inverse that exists. But we can do something called the pseudo-inverse, which you get by doing a truncated singular value decomposition of this kernel, and that allows you to take some steps towards getting a solution from the signal by doing this pseudo-inverse here. Now, that is sort of an approach that's been known for decades, and if I take, for example, what I call a model here, a bivariate normal distribution, which we'll call the ground truth distribution, and we predict a spectrum. So this is an MAS spectrum here. So we can do this with sidebands or off angle. It doesn't really matter. And so in this case, we're predicting an MAS spectrum, and we add some noise to it. And we're going to try to use this spectrum and that pseudo-inverse to turn this back into that distribution. And of course, the result of that is this here. So this is the truncated singular value decomposition solution, and you can see there's some problems there. It creates intensity all over the place. In fact, you even have negative intensities. And so what we need to do is come up with a penalty function to eliminate these unphysical solutions. And this is the solution that we have. This is the penalty that we have. So our penalty then is going to involve this least squares approach with the penalty added that looks like this. Now, I'm not going to get into the details of how we arrived at this, but there's a really nice talk by DePonch at the Global NMR discussion meeting. There's a YouTube video that you can find, and he describes a lot more details about what's going on here. But let's just leave it at the fact that there's two terms here, and this term here, which is what's called an L2 penalty, controls the smoothness along the x and y dimensions, and it promotes smoothness along those dimensions. And this term here will promote sparsity in the whole solution. And so there's two what are called hyperparameters here, alpha and lambda, and tuning those parameters will tune the amount of smoothing or the amount of sparseness that you're looking for in your solution. And glasses and amorphous materials will tend to have bigger values of alpha than, say, a crystalline material will. So if we use this, the ground truth distribution, if we invert that spinning sideband pattern, if we get this for our inversion, and it compares very nicely to our ground truth. So if you go back to the previous slide, this is what we got by inverting this spectrum. Using this penalty function, this is what we get for inverting that spectrum. So it works really well, at least in this case here, but I can show you some more examples here in a bit. Now, one of the things that you have to do is you have to tune the hyperparameters, and the way that's done is with something called tenfold cross-validation, and you can get more details on this just Googling around with some various textbooks or looking at scikit-learn. And the general idea is that you vary through alpha and lambda, and you look where a cross-validation error function will go to a minimum, and then that will be defined as your best inverse solution here. Again, check out DePonch's video on YouTube for more details on all of this. So here is another example. These are ground truth distributions that we use to simulate NMR anisotropic cross sections, and these have three different, sort of a trimodal distribution, three different types of distributions in each one. So here are the 1D anisotropic distributions that you generate from these ground truth distributions, and then inverting these with the smooth lasso algorithm gives us back these distributions, which you can see are pretty close to what we started with. Similarly, if you're working with spinning sidebands, here is the it's simulated spinning sidebands from this with noise added, and here are the inversions you get. Now, back to the glass problem. If we're going to look at these different Q species, their anisotropies are going to live on this XY grid, and the way they'll appear is that the Q0 and the Q4 will show up down here near the origin, and it turns out actually that there's often, we're finding more disorder in Q0, so Q0 tends to stick out a little bit further than Q4 from the origin. The Q3, which has the positive anisotropy, shows up over here. The Q2 will show up sort of in this region here, and the Q1 will show down here. Now, how far they extend out in this direction depends on how much of a deviation there is between the bridging and non-bridging oxygen bond lengths. So that's where we expect things to sort of lie. Here is a sodium silicate glass that we ran a magic angle flipping experiment on. Here is the corresponding inversion. Every one of these cross sections are inverted, and actually they're inverted independent of each other. And when you do that for every isotropic position, you end up with a 3D distribution of amplitudes for isotropic X and Y, and this is the result here. This is a 3D plot. And you can see here's the Q4 cloud, here's the Q3 cloud. If you project out the isotropic dimension, you can see here's the projection on the XY plane. This is a region down here, which I said previous slide was associated with Q4s. Here and then here you see the region which is associated with Q3s, which is over here. And here we have then a much clearer separation and assignment of these peaks here in this distribution. What's really fascinating is that you can see in this that the method actually learns about distributions that are check-like and even extended check-like. So we didn't have to use any explicit check model to fit the glass. The approach was able to look at the glass spectrum and find distributions that actually turn out to be very much like a check distribution. What's also useful is that particularly when these are well separated like this, you get much better populations. If you use any kind of explicit analytical model, there'll tend to be some cases where it doesn't fit exactly, so you sort of have some lost amplitude, and so some of your populations might not come out as well. Here we get much better fits, so we get populations which we think are a little bit more reliable, but they're pretty close to actually what Jay Baltusberger found in his analysis in this older paper here. Now, the other interesting thing you can do is you can get out of that XY plot and you can go back to a 2D plot where you project out the eta dependence. And here's a plot of isotropic shift versus shielding anisotropy. And this is for the sodium silicate glass. And what you see is this interesting behavior here. First of all, for the Q4, this is what I call check-like distribution looks like for Q4. You have random distortions away from a perfect tetrahedron, which is what's happening in the Q4. And that random distortion leads to sometimes positive zetas, sometimes negative zetas. And so you get this distribution where it's centered about zeta equals 0, but it's peaks on both sides, so it's bimodal. And that's sort of expected for this Q4 shielding anisotropy. You also see that there's some shape to this. You can see that the width of the anisotropy at different points in this line is changing. And what we think is going on is that as you move along the isotropic dimension, we think we're seeing Q4s which are surrounded by varying amounts of Q3s, and that's leading to this sort of broadening out. And then when you get over here to the other side, it starts to narrow back up again. For the Q3 distribution, well, this is more, as I said, extended check-like. And here you see that there is a decrease in a little bit slight decrease in the zeta as you increase the chemical shift. And we expect that there should be some variation there too with increasing isotropic chemical shift due to changes in the next nearest neighbors there. But details on what those structural origins are something we're still kind of working on. If you look at various types of different compositions in these delta zeta plots, so to speak, you can see the variation here. You can always see the Q4 here. In this composition, it's a much lower silica content, so you can just barely see the Q4 here. And you can see that there are some clear variations in the Q3. You can see this Q3 is peaking at a different position than the Q3 below it. Similarly over here, this one is moved over compared to that one. And so there are all kinds of details going on in the shapes of these that we're still learning about, but we can see something that's really, we believe, is related to structure. If you take the projections of those shielding anisotropies for the Q3 sites, and you use that relationship that we sort of proposed earlier, sort of rough relationship, you can see that the change in those peak positions is just really telling us about how the silicon non-bridging oxygen bond length is changing in these different compositions here. The Q3 distribution also has some width associated here, and probably it's, in these cases over here, that width is mostly the silicon non-bridging oxygen distance variation. But in the case of this magnesium, potassium-magnesium mixed glass, modifier glass, we think some of this width here is really due to Q3 tetrahedral distortions that's leading to this. So it's not just always this. There could be other factors that are playing into this width here. And then sort of final example I'll show is this calcium silicate glass. Again, this is older data that we have from the 90s, and this was silicon 29 enriched data set. And this is where you have calcium, and calcium has such a high potential that it causes much greater depolymerization of the network and also more distortion of the tetrahedra that are present. So you see in this glass actually indications of all 5 different types of Q sites here. And now if I showed you the 3D inversion, it's just like one big cloud. So I'm just going to show you cross sections here. So you can see here at isotropic chemical shifts associated with Q4, you can see the Q4 XY cross section here. Here you can see for B, we're starting to get into the Q3 region. And then for C, we're down here in the Q2 region. And D, we can see evidence. Now we've flipped over to the other side, it's Q1. And then when we get down here to E, we're starting to see what looks like Q0 type distributions there. And so there's, again, lots of information in here. We're still working out ways that we can sort of improve our quantification when they have overlapping distributions like this. But it's definitely nice to see that we can do this without building very explicit models for the distribution of shielding parameters. So let me just conclude here by saying that this smooth lasso inversion is really fairly robust in getting the 3D distribution of tensor parameters. There's all kinds of subtle details about the glass structural distributions that we can find in these inversions. And it's not just limited to the CSA. So for silicon 29 CSA, we've shown nicely that it works, but you could also do this with quadrupolar coupling constants. Say oxygen 17 is one that we're really excited about. And the other important thing is that we have a Python package. DuPont has put together a very well documented Python package so that you can actually do this with your own spectrum. Even if you don't have a magic angle flipping probe, which most people don't, you can do this with 2D pass or 2D mat, and he has code in here to invert those spectra also. And that sort of brings me to a last couple of points I want to make, is that we've been developing a number of software packages in Python to sort of integrate with the sort of all the other tools in the Python world to help us analyze better all of these types of NMR, multidimensional NMR spectra. And so MR inversion is a package that integrates with many of these other tools. And there's 2 other packages that we've developed along the way that are really important I just want to tell you about. And so, of course, first of all, there's the MR inversion package, which you can get the code at GitHub. You can just go into the Google Colab and install it with pip install MR inversion and read through the docs. And you can work through all of the examples that I showed in this talk are present here. You can download the data, you can invert them yourself and see how all of this works. But part of writing in MR inversion required a lot of line shapes to build those kernels. And so for that purpose, DuPont wrote a general package called MR Simulator, which will simulate all types of solid-state NMR line shapes very, very rapidly, much more rapidly than you could if you were just using something like Simpson or spinach. And this is done so that we can generate these massive kernels to invert our glass spectra. So there are limitations. It's not going to work like Simpson or spinach in terms of the versatility, but for the type of 1D and 2D spectra that we need for these type of things, it's very, very fast, and you should check this out if you have a chance. Additionally, during the whole process, we needed some kind of file format to store all of these multidimensional data sets and their inversions, and we realized that that file formats such as JCamp were really old and not modern and not really working the way that we needed them to do for the kinds of 2 and 3D, 4D types data sets. So working with Tomas Vosegard and Dominic Massiot, we developed this core scientific data set model, which is very versatile, and I really encourage you to take a look at this and use this, particularly if you're interested in your data management plan for your grants and you want to find a nice fair data set file format. Take a look at this. We have a Python library here for using it, but you can use it in other places also, and it's very useful and integrated with all these other applications that we've done. And the last thing I'll mention is that DuPont is also working on taking the MR Simulator library and integrating it together with a web app that you could run on any of your portable devices or on your desktop or laptops. And this is really exciting. We're looking to maybe release that later this summer. So I'm going to end this here, back with my original summary here, and also say that if you would like us to come and visit your group meeting and a Zoom tutorial, we'd be happy to tell you about any of these packages. Thank you for your attention.